Oh.
My sister's
Oh, her tardy. Did she come in with you?
Yes.
Yeah, that's why. Yeah, her tardies are your tardies. All right. All righty. So the one thing that we didn't see was what to do when we complete the square with where your coefficient is not A. I don't think they would ask something like this on the AP test because this is the kind of category that it's just like one question, check to see you know how to do it, things like that. So let's take a look at this one. We were using the formula, the thing that we were adding and subtracting when A was 1 was B equals, no, it wasn't B equals, sorry. It was B over 2A squared. I wasn't set equal to anything. No, it was just B over 2 squared, right? Sorry, my bad. Yes, B over 2 but squared, right? That was the thing we were doing yesterday. But we said that A is equal to 1. So somewhere inside there's a 1 being multiplied that we don't see. That's generally how things work in math. If we work out to a less specific case, a lot of times something was just kind of hidden in there. And the idea being that if I need to complete the square with 4x squared, that means that I have 4 of these blue blocks. Kind of showed this to some people who were looking yesterday. I have 4 of these blue blocks. And then I've got to take all of my x's, which in this case I have 12 of them. And I think that's exactly how many of these green guys that I have. And I have to split them up evenly to make a square. So the idea is I'm actually putting 2 here and 2 here. So that B over 2, the thing that we were doing yesterday that was B over 2, is the math that figures out, you know, kind of how many to put here so that I get a total of 12. And it turns out the way that this picture would look, and you can grab my last 4. We're completing the square? Were you here yesterday? No, okay. So these blue blocks represent x squared. So I have 4 of them. That represents my 4x squared. The green rectangles are x by 1. So we're considering this length 1 unit. So those are x by 1 rectangles, and I have 12 of them. So my picture on the board is 4x squared plus 12x. So what we have to do here, the way that we get this, what we're trying to figure out is that we have, what we want to figure out is that we have to go 2 by 2 and then have basically 3 of them. So what we do is we take our b, and in this case we divide by 2 square root of a. That's what gets us this answer. 2 square root of a. And in this case, what you'll see that happens is you get 12 over 2 times 2, which is 3. So that really is what we're trying to figure out, is how many there are in each, off of each square, I should say. So how many greens there are off of each square? 1, 2, 3. You do that by taking the 12 that you have, dividing by 2, because for the first time you're dividing by 2 because you need to put half of them on the right and half of them on the left. And then dividing by 2 again because half of them go with the top blue block and the other half go with the bottom 2 block. And that will work no matter what. Like, this math summarizes the picture to figure out how many green things we have in any given location. All right. So with that being said, we need to square that, because our real goal here is not to figure out how many greens there are, but how many little yellows we need down here, right? And what's missing here is 9 little yellows. Our square is complete, which is why we call this completing the square. If you're watching the video, you're missing me fumble with magnets on the board and things like that. So we have this but squared, we have this but squared, so our number is 9. So our integral is really negative 4 over 4x squared plus 12x plus 9 minus 9. Oh, yeah, I got to move those, don't I? Yep. Plus 13 dx. Yep. I was thinking that as I was. All right. Yeah. This is why I had 13 yellows on the top, because of this problem. So I didn't lose anything from last year. Okay. Boom. Okay. Which, when we simplify that out, when we actually do the two things that we do with it, where did I put my pen at? We are going to factor 4x squared plus 12x plus 9. That's going to factor to a perfect square. So really what you're doing is you're taking the square root of your A term and you're taking the square root of your C term to figure out what the factorization is. So this is 2x plus 3, the quantity squared. I think this is how I did. Let's do colors here. So we got this. We'll write that as 2x plus 3, the quantity squared. And that is my picture. If you go down or across either side of it, you have 2 lengths that are x, and you have 3 lengths that are 1. So 2x plus 3 by 2x plus 3. This is a 2x plus 3 square. So the algebra that it represents is 2x plus 3 squared. And then we combine the negative 9 and the 13 to give us plus 4. And we are hoping to have a perfect square there. Otherwise, the math ends up ugly. Okay. Keep in mind, the thing that we had at the beginning was 4x squared, 4 blues, plus 12x, 12 greens, plus 13 yellows. 9 here and 4 here. That's why we're doing this part right here. We're taking 9 away from the 13 to complete the square. Okay. All righty. All right, fun. So let's get this right. We need a u sub, but since it's trig, we're not going to start with u, we're going to start with u squared. So in this case, our u squared is, u squared is 2x plus 3 squared, which makes u just 2x plus 3, which makes du 2 dx. But I don't have 2 dx, I have dx. So I'm going to multiply both sides by negative 2. So we got negative 2 du equals negative 4 dx. Didn't do a good job of color coding this part. Let's just change. Nope, that's the wrong one. Look at that purple-ish. Right. A lot of color coding and a lot of color coding for different reasons. So, all righty. Which makes our final integral in blue, negative 2 out front, or negative 2 in my numerator, however you want to do it. I'll do a 1 to placehold. And we've got u squared. Oh my gosh, this is brutal. I should have done something before I did this. Yep, I should have taken out the 4. It probably actually makes life easier. Let's take out the 4 and erase all this. I realized that I wasn't going to get a must know there. So, yep. Yeah, so we will factor that 4 out to give us the integral of negative 4 over 4, the quantity 2x plus 3 but squared over 4 plus 1 dx. I don't know what that means. But why am I taking a square root? But we divide to simplify. I'm going to simplify this way. That's what I'm going to do. All right. All right. So now to fix this up, now correctly my u squared is 2x plus 3 but squared but over 4 as well. So, which makes our u 2x plus 3 over 2, which is just x plus 3 halves. Which makes our du yeah, well, 1 or just dx. Yep, don't put the dx, yeah. Yep. Yes. So yes, that 4 at the end. You know, when you get 1, it's nice. When you complete the square and there's 1 left over, it's nice. When you complete the square and there's a different perfect square there, less nice. But that's why that 4 was in the numerator in our original problem, to make our life, I don't want to say to make our life easier, because nothing's easy here. So we end up with something that is a must know. There is a negative out front. Good for that. 1 over u squared plus 1 du. Yep. Which is the negative arctan of u plus c, which is the negative arctan of 2x plus 3 over 2 plus c. All right. And that's the one above the one that says some big kid examples. I don't know if we'll do all of the big kid examples. I don't think they're all necessarily on the ones that you have to practice later. So we'll only look at a couple of those. I think my last example here, if I'm not mistaken, I didn't do it, but we'll do it now. I think this is actually an anti-example. I think this is one that we are not, this is actually going to be one where we are not going to be able to solve. And in AB, we won't learn the technique to solve it. One of the things we wrote on our card yesterday was that in order for the completing the square technique to work, your denominator shouldn't be able to be factored. Can I factor x squared plus 4x? Yeah. Absolutely, right? I can take an x out of that. That's x times x plus 4. So that's a different technique that you'll see if you take Calc 2 in college, called partial fractions. But it really is, that's kind of like the split between these two. These go one way or the other, and we only learn the completing the square in AP Calc. But let me show you what happens if you try to complete the square on this one. So a much easier one, we'll do 1 over x squared plus 4x plus b over 2 squared, which is just 4, right? I'll cut it in half and then square it. Because it was 4, it ends up back where it started. So I need a plus 4 minus 4, and then I'm done. Because there was no number there to begin with. So you end up with the integral of 1 over x plus 2, but squared, minus 4 dx. And the problem with this is, if I do what I did, which would be to factor out just a 4, then I'd have u squared minus 1, which is not a must know, right? Because it's u squared plus 1. If I factored out a negative 4, it would be negative u squared. I couldn't make my u squared negative x plus 2 squared, because then I couldn't take its square root, because I'm taking the square root of a negative. So this is, not solvable by completing the square. I have the feeling at some point I'm going to have to show Jack partial fractions. It's actually easier. I kind of wish partial fractions was the AB topic, because I feel like this is our most complicated process by far. And the most little spots for things to go wrong. All right, let's take a look at our big kid examples. I actually feel like the first one and the last one, unless I'm missing something, are kind of the same idea. Let's look at the one on the right. This is the one I kind of want to spot. If there's anything that I think you might see or I might expect you to know, it would be one like this. One of the things that I kind of left out, and on Monday when we do the speed integrating. By the way, before I forget, if you know you're not going to be here on Monday, please let me know at some point ahead of time, because it'll be the thing where we're doing the pairing ups and switching around. So try to be here every day, but especially on that one. And if you know you're not going to be, just so I have it in my head how many students I'm going to have, I would really appreciate that. But anyway, so back to this one, looking at the second one first, and then we'll work our way over. And I feel like the last one's, unless I'm missing something, kind of just a more complicated version of the first one. If you're just thrown an integral at you, in this class, we've seen all of our techniques. In BC, there's 2 or 3 more techniques you might see. So in Calc 2, there's those techniques you might see, and you've got to figure out what to do. The first thing you should really eliminate is U sub. That's really the starting point for most integrals. Is there something you can find its derivative of? And that's really what this is going to end up being, U sub. But we have to figure out what our U is. We're looking, sorry, no, yeah, I know, I've been saying it, but I'm looking at this one. My bad. Yeah, I know, I've said I'm going to work my way over, but I'm also visualizing that in my head. So yeah, we're looking at the one that has e to the x in the numerator. It's going to be U sub.
Okay, so after reducing.
Mm-hmm. So I heard a U squared. What would you make your U squared? E to the 2x, yeah. If you make your U squared e to the 2x, then what's your U? E to the x, yeah. So watch out for things being squared, and especially in this case with e to the 2x, this is kind of testing that you realize that that's not a pen, that's still not a pen, e to the 2x is the same as e to the x, but squared, because that's exponent rules. A power to a power, just multiply those 2 powers. So you make your U squared equal to that, which makes your U just e to the x, because you take the square root of it, which makes your du in a different color, e to the x, dx, in the language of integrals. And then it's ex dx u squared. Yep. So it literally is just the integral of 1 over 1 plus u squared dx, which is arctan of u. Yes, thank you, du. Arctan of u plus c, which is the arctan of e to the x plus c. Oh, I know. No, the bottom one is different. Yep. Okay. Okay, so looking over at the example at the left, same idea. We want to think U sub, and we get really close here. But we're actually going to do kind of the trick that we use, not trick, but technique. The technique that we use with completing the square, but we're actually going to do it in the numerator on this one. So here for our example, our U, well, if we're doing U sub, what would we kind of want to identify as our U? Yeah, identify the denominator. And that gives me a derivative of 2x minus 2 dx, but I have 2x minus 1 dx. Watch how we can still actually do this. So I'm still going to identify my u as x squared minus 2x plus 2. That's what similar. My du is going to be 2x minus 2 dx. Oh, they're going to ask us for money again. Just tell them we're yeah. Nah.
Okay, any money for you,
Sorry. One day maybe, but probably not. Yeah. All right. Yep.
Yeah, and I'm just putting it right back in your bag.
So what we're going to do is we need to think. Yeah, we are going to do that. So we are going to rewrite our integral as the integral of 2x minus 2 plus 1. Yep. So I didn't show the add 1, subtract 1. I'm just trying. I need that numerator to still be equal overall to 2x minus 1. So I'll make it 2x minus 2, but then I'll put a plus 1 there. So I don't know why I changed my color on that one. I'm going to make that back to orange. Sounds about right, yeah. So we got x squared minus 2x plus 2 dx, which really means I have two separate integrals to solve here. I've got the one that I'm going to u sub, which is 2x minus 2 over x squared minus 2x plus 2. And then I've got a second integral, which I'll be able to complete the square on. So I think I'm going to leave this example as this in the idea that I want to give you more time to work instead of more time for me lecturing. So we'll say that this is our u sub integral, and this can be solved by completing the square, I think. It can be. I think actually, I actually don't think I have that last number written out so that it comes out nice. So I'd have to do plus 4 minus 4. You'd actually end up with a square root as part of your coefficients. But yeah, I should change that one for next time around. But yeah, so both of those can do that. Like I said, usually the numbers work out nice for completing the square. You can complete the square on this one. It's just that your numbers, actually, plus 4 minus 4 on that one. Yeah, I really should change that last number to something else. It wouldn't affect most of the problem because when you do the derivative, yeah. The first one does just come out to LNU. You're right. Yeah, that first one's LNU. And the second one actually should be completing the square, but I'd have to change the number to something like plus 6. So that's, yeah. No, just make them all 6s where all the 2s were. Bad problem. That would actually be partial fractions. Plus 6. No, not plus 6. Make it plus 8. Yep. I'm not going to finish the problem anyway, so this will only come into play if you're Jack and you actually want to finish it. So, yeah. So yeah, so Jack can solve that problem. The rest of you can be just happy in the knowledge that the first one could be just u subbed, and it's actually really simple. As Franklin noticed, it was LNU. And then the second one is just one more practice problem for completing the square. If you feel like you need one more practice problem for completing the square. I know. I keep thinking. Yeah. Cool. All right. I'm going to leave it at that one. I'm not going to do the last one. I think there's two ways to do it. I think you can do it with long division, and I think you can do it with u sub. So it doesn't feel like a very different answer. I feel like it's going to have the same result. We're going to have one u sub integral plus another completing the square integral. So yep. I had put higher on the thing, but the very first example you guys did, they were the same. So it's higher or the same. It's really that the denominator can't be lower. So I gave you the wrong. I missed the or equal to of it all, and yeah. All right. Yep. Okay. So with that, I'm going to stop